I'm Kathiresan, working as assistant professor in Department of Mathematics, College of Arts and Science. Today I'm going to handling a subject, modern algebra. So the group theory and its application. So what are the table of contents? So first thing we are going to discuss about the modern algebra. So how the modern algebra get the name, and the second one is the definition of groups, and the third one is order of a group or order of an element of a group, and the fourth one is modular arithmetic, and fifth one is subgroup, and the Lagrange's theorem. Lagrange's theorem, which is nothing but this is a fundamental theorem of algebra, and the seventh one is Sylow's theorem, and the applications about the Lagrange's theorem and the Sylow's theorem. Okay, now the first one. Okay, what is the first thing? What is modern algebra? Modern algebra is nothing but, which is also called an abstract algebra. So abstract algebra, which is a branch of mathematics concerned with the general algebraic structure of various sets. What are the various sets? Like real numbers, complex numbers, and the matrices and the vector spaces. So which is the pure mathematics paper. An abstract algebra will be called as pure mathematics paper, and which is nothing but we are going to using the algebraic structures including the groups, rings and fields, modulos, vector spaces, lattices and algebras. Okay, let me go to the next slide. What is group? Group is nothing but let G be a non-empty set and star be the binary operation defined on the structure. Which structure? G comma star. G comma star is said to be group. When will be that G comma star is said to be group means it must be satisfies the four following properties. So what are the four following properties? Closure property, associative property, and existence of identity and existence of inverse. So now we are going to testify what are the axioms and how that four axioms will be satisfied under this binary relation star. Okay, now let's talk about the closure property. What is closure property? A star B, it belongs to G. For all A comma B is belongs to G, which means that we are going to take an element A B belongs to G for all A comma B. So let me take an example. I will take A1 comma A2 means then A1 star A2. The star is nothing but the binary relation, the binary operation. What are the binary operations are there? Addition, subtraction, multiplication, division, like that. So the two elements we are taking in G, that must be the the binary operation will be applying that operation A star B that belongs to G means then the closure property will be satisfied. So like that, then the associativity also, the operation star is associative in G, that is A star B equal to A star B star C, A star B star C, which is equal to A star B star C for all A comma B comma C belongs to G. Now the existence of identity. So the closure and associative will be looks like the same, but the associativity for the three elements A star B star C, which is equal to A star B star C. Then the third one, existence of identity. How we are proving the existence of identity? Identity element in a group, that must be 1. So how that identity element will be exist in the group? How we are going to find out? Using this condition, A star E, which is nothing but A, or E star A, which is nothing but A. Whenever we are going to multiplying a number or a single element with an identity, we are getting the same element means then that should be called as identity. So here the E should be the identity. When we are multiplying an element with identity, we are getting the same element. When we are multiplying means like while I am telling multiplying means when I am taking the binary operation is multiplying, this should be multiply. When I am taking the binary operation is addition, then here should be addition. When I am taking this binary operation is subtraction, here should be the subtraction. Like that, a binary operation A star E, that should be A, and E star A, that should be also A means then that E should be called as the identity element. Now the existence of inverse. Inverse. What is the existence of inverse? For each element A is belongs to G, then there exists a unique element. For each A, whatever I am going to taking in A, there exists a unique element which is called as B, then A star B equal to we are getting the identity, or B star A we are getting the identity means then that B should be called as a inverse, that B is called as inverse of an A. Then this is like existence of inverse property. So let G be a non-empty set under the binary operation star. It must satisfy the four condition: closure, associativity, existence of identity and existence of inverse. Means then that G non-empty set should be called it as group. Here the G non-empty should be called as group. Okay, how we are going for the abelian group? Abelian group is nothing but we need another more property. That property should be called it as a commutative property. A star B equal to B star A for all A comma B is belongs to G. So this is called as abelian group. When the group having a fifth property, commutative property, means then that group should be called it as an abelian group. Okay, now here are some examples of group. Let 3 cross 3 matrices with real entries. These are all entries will belongs to the real numbers. So this group sometimes will be called it as Heisenberg group. So why this group called as an Heisenberg group means, after the Nobel Prize winning physicist Werner Heisenberg is intimately related to the principle of quantum physics. So that's why this set of all 3 cross 3 matrices with real entries should be called it as Heisenberg group. Now let me take in another example. This is the example of a composite function, which is what is composite function is the multiplication between the two functions, that is called as composite functions. So here is the example of the non-abelian group, finite non-abelian group of order 6. So f1 is z, f2 is nothing but 1 by z, f3 is 1 minus z, f4 is z by z minus 1, f5 is 1 by 1 minus z, and f6 is z minus 1 divided by z. Okay, what is order of group? Now we move on to the next topic. Like we are already discussed about what is group. Now order of a group. How we are going to defining the order of a group? Let me tell you. The number of an element in a finite group is called the order of a group. When we talk about a group, there we are having like a finite number of element in a group, means in a particular group. Then that should be the order of a group, and it was denoted by the order of G. When we talk about an infinite group, means it has an infinite number of elements. So infinite group is nothing but it has an infinite order. Okay, I will give you some examples. So here see the first example. Let G equal to 1 comma minus 1, then G is abelian group. This one is an abelian group with respect to the multiplication. So what is the order of this one? We are having only two elements, 1 and minus 1. So that's why the order of G must be 2. Now the second example, this set Z of integers is an infinite group. We already know that Z is an infinite group, but with respect to the operation of addition only. But Z under the multiplication, which is not a group. Why? Why Z is under multiplication, which is not a group, means under the addition, we are talking about under the addition, the identity element will be 0. When we are talking about 1 minus 1, when we take in element 1, the inverse will be minus 1. When we are taking like 2, the inverse will be minus 2 for addition. For multiplication, when we are talking about an identity element, it should be 1. So let I am taking like 2 is the element from Z under the multiplication. I need an inverse that should be 1 by 2, but the 1 by 2 is not belongs to the Z. So that's why Z is not a group under the multiplication. Okay, now order of an element of group. Okay, let me talk about order of an element. Don't confuse about like order of a group or order of an element of group. Order of a group is nothing but the finite number of elements in a group. That should be the order of group. But order of an element is we are going to testifying the specific element, not only the entire group. We are talking about the specific element only. So let me take let G be a group under multiplication. Let E be the identity element in G. Suppose I am going to take an element A in G, then at least positive integer n, a least positive integer n, if there exists, this one is an important one, if there exists an A not equal to E in such that A power n equal to E, means then that should be called it as order of A. So I will give you the examples. So what are the example cases is, here is the multiplicative group, which is nothing but G, 1 comma minus 1 comma I comma minus I. Okay, let me tell which is the fourth root of unity and have an order of its elements. How we are going to find out the order of an element? So we are going to using this definition. What is the definition given? A not equal to E in such that order of A that should be this a power n, that should be e means then that n should be called it as order. So when we are operating the element, we are getting an identity element means then that should be the order. So here one should be called as like identity element having a order 1, but minus 1, when we are operating the minus 1 like multiplication, under multiplication, minus 1 into minus 1, it should be the 1. So the identity element exists only for the minus 1 into minus 1. When we are multiplying with minus 1 and minus 1, we are getting the plus 1. So plus 1 is the identity element. So the minus 1 order of this particular specific element is 2. So like the same concept, I power 4 is 1 and minus I power 4 is 1. So the order of I should be 4, the order of minus I should be also 4. Now we step into the next example. So what is the next example? The additive group. So additive group is nothing but is that the order of 0 is 1. It is a finite one, because order of 0 is finite means because 0 is an identity element. So the order of a should be the infinite. Now the modular arithmetic, so which is nothing but the modular system, a congruent b mod n, which is nothing but an addition modulo is a plus addition modulo b equal to r, a multiplication p b equal to r, which is called as r is a remainder, and a plus b is nothing but a plus b divided by m, a multiplication b divided by p. So that's the thing here given, and here is the example for the modular arithmetic, the Fermat-Little theorem and Euler's theorem. So let me move on to the next topic, which was called as subgroup. So how we are going to proving subgroup? Subgroup is nothing but a non-empty subset H of a group. Then it should be a subgroup means it must satisfy the two conditions, that must be like a closure property and inverse. If it was a finite group, then G is a finite means we are going to proving the subgroup means we need two conditions only. Those two conditions are called as closure and inverse. Okay, what is the next one is an important one. What is Lagrange's theorem? Lagrange's theorem taking a big part in group theory and its applications. What is Lagrange's theorem statement says? The order of each subgroup of a finite group is a divisor of the order of the group. Okay, when we are taking like order of G equal to 1 means then order of H equal to m means this m it should be divides this n, which means that the m is the divisor of the n, then only the Lagrange's theorem will be true. Okay, I will give you an example for the Lagrange's theorem. Here in the example we have some here the G equal to 1 comma minus 1 comma I comma minus I, which is having a group of order will be 4. So what are the divisors of 4? 1, 2, 4. So 1 divides 4, 2 divides 4 and 4 divides 4. So this is the example case for the Lagrange's theorem. Now converse of Lagrange's theorem is not true. Why the converse of Lagrange's theorem not true? Which means that whatever I am going to divide order of G divide means that doesn't mean it has a subgroup of that order. So I am having an example, a symmetric group of A4, which is nothing but 12, the group of order 12, but it doesn't have any subgroup of order 6. So which is an best example for the converse of Lagrange's theorem. And Sylow's theorem, which is an important one, even though while in NET exams and GATE exams the Sylow's theorem will be the important one. So what is the Sylow's theorem says? The order of G equal to p power m, then p power alpha divides m, but p power alpha plus 1 doesn't divide the order of G. So that will be called as p Sylow subgroups. Okay, now the Sylow's theorem, here is the p power m divides order of G, but p power m plus 1 doesn't divide order of G. So which is called as p Sylow theorem, first theorem. So we are having an example for the second Sylow's theorem. The second Sylow's theorem is nothing but the continuous of the first Sylow's theorem, which is the statement of let G be a finite group and P be a prime number. P divides order of G means then we are taking any two Sylow P subgroups that must be the conjugates. We are taking any P Sylow subgroups that must be conjugate is the statement of the second Sylow's theorem. And third Sylow's theorem is the important one for the NET exams, GATE exams. So what is the statement of the Sylow's third theorem is the number of Sylow P subgroup in G for a given prime is form of 1 plus kp where 1 plus kp divides order of G. So, which is the best example for the Solo's third theorem and Solo's first theorem and Solo's second theorem. It might be useful for the futures also. These are all the applications for using the group theory and its applications. I hope the class will be grateful. Thank you all for watching this video.